We found earlier that the Poisson distribution was a limiting distribution of the binomial, and that the binomial was a limiting distribution of the hypergeometric. The normal distribution also can be shown mathematically to be the limiting distribution of the binomial and therefore used to estimate probabilities from a binomial process. An example may help here. Question: what is the probability of throwing a coin 100 times and getting more than 60 heads? This is clearly a binomial process because the outcomes are either success, heads, or failures, tails. And the probability of success is constant from trial, that is to say a flip, to trial. To solve this using the binomial formula, we would have to solve the binomial equation 40 times, and remember the addition formula, and add these all up. Okay. The question really is, what is the probability of getting 60 heads, or 61, or 62, etc., to 100? This means that we have to solve the binomial formula 40 times. Here is a statement of the problem. The probability that x is equal to or greater than 60 is equal to the probability that x is equal to 60 plus the probability that x is equal to 61, that's a 1, plus ... all the way to probability x is equal to 100. Okay? Using the normal distribution, this becomes an easy problem to solve. Recalling that the mean and standard deviation of a binomial distribution are given by the formulas mu is equal to np, and the standard deviation is equal to the square root of npq, we can calculate what the mean and standard deviation are of the binomial problem. Now we can lay this out as follows. Here I have x, which is number of heads. That's our random variable. Now I'm going to write this as a normal distribution. And up here, I always like to put the standard deviation because that helps me remember what it is that I'm doing. Down here, of course, I have the mean. So the mean is equal to what? Well, if we have 100 and the probability of hitting a head is a half, then this is going to be equal to 50. So this is 50 here. Here I'm going to substitute in n, 100, times 0.5 times 0.5. So half of 50 is, half of 100 is 50. Half of 50 is 25. Square root of 25 is equal to 5. So my standard deviation is equal to 5. The problem then becomes that the probability that we're interested in is that x is equal to or less than 100 or equal to or greater than 60. And that's what we're after. Down here, what I can do is I can link the two together. This is the z-axis, or the standard normal distribution. I can go down like this. I can draw myself my distribution. And up here, I will take these values. This is going to be 60 here. There's 60. And I want all the way to 100. Okay? Another way I could write this thing would be probability that x is equal to or greater than 60. After all, if I'm only flipping it 100 times, I don't really need to notice that. So what I have down here is this question. This is 0, and this is z1. We simply take our standardizing formula, and we figure out what z1 is equal to. z1 is equal to the x minus mu divided by standard deviation. So in this case here, this is going to be equal to, I'm running out of space, but I'll stick it down here. So I've got x is equal to 60 minus the mean 50 divided by the standard deviation 5, and that's equal to 2. So this number here is equal to 2. All I'm asking for is the probability that x is greater than 60, which is equal to the probability that x is greater than 2 standard deviations. Another way of writing this would be the probability of z equal to or greater than z1, which is, in this case, 2. This area and that area are the same areas. I need to go to the standard normal table and look up what this probability is. Okay? Now, the way the table is set up, it gives us this area here. And I look up that area. And so if I go out 2 standard deviations, I find that that area there is equal to 4.772. I am interested in this area. I know that half of it is on this side because it's symmetrical. Therefore, to get this area here, I simply take 0.5000, subtract off 0.4772, and I ought to be able to now get my answer, which is 0.0228. Okay? So the probability that I'm after is probability that x is equal to or greater than 60 is equal to 0.228. Not a very probable event, as we note. In practice, the normal distribution is used to approximate a binomial when n, p, and, both of them have to be the same, and nq are greater than 5. The reason that both conditions must hold is that as p deviates from 0.5, the binomial distribution becomes skewed. Because the normal distribution is a symmetrical distribution, a good approximation cannot be developed if the underlying binomial distribution is skewed. As a more interesting example, here is a relevant problem that uses the normal distribution to estimate what is clearly a binomial process. Mike has been hired by the bookstore to do an analysis of book buybacks. He finds that the probability of someone selling their books back at the end of the semester is 0.75. The store manager wants to know if 300 students buy books this semester, what is the probability that at least 220 students, but no more than 235 students, will sell the books back at the end of this semester? The results help determine how many new books to order. We see that this is a binomial process. The students either sell the books back or not, and the choice is independent of each other. To use the normal distribution to estimate this binomial process, we first must determine if the requirements for making an estimate are met. Specifically, are NP and NQ greater than 5? This is our rule of thumb for allowing us to use the normal distribution to estimate a binomial process. And we can see that they are. NP is equal to 300 times 0.75. And Q, of course, is equal to 0.25. And we have, again, 300 times 0.25. These numbers are both greater than 5. Indeed, this is 225, and this one here is 75. Okay? The next step is to draw a graph and visualize the question being asked. Okay? And so here we have our x, which is the random variable, is number of books buyback. Okay? This is drawn as a normal distribution, and it has a mean here. Now our mean is equal to NP, which we've already calculated. So there's our mean of 225. The probability question we are asking is this. It's the probability that x is equal to or less than, and I have to check myself here, is equal to or less than 235 equal to or greater than 220. Okay? So I can mark up here 235, and over here 220. This is the probability we're after. This area here and here. I'm going to mark these out separately because we'll see shortly that we're going to have to find each one of them separately. Okay? Now, what we can do underneath here is we can draw the normal distribution. Here is z. This translates down to here. Of course, the mean of the normal is 0. Here's our normal distribution. Looks like this. I translate this down to here, and I translate this down to here. This one here, I'm going to call Z2, and this one here, Z1. We now take and find the following. The probability that x lies between 220 and 235 is equal to the probability that z lies between z2 here and z1 here. So now we have to calculate our two z values. z1 is going to be equal to x1 minus mu divided by the standard deviation of the sampling distribution. Now we have to find the standard deviation of the sampling distribution, sigma. We'll remember that sigma is equal to the square root of NPQ. If we calculate that, we'll find that standard deviation is equal to the, and I have to find myself here, is equal to 7.5. Okay? So this is going to be equal to z1 is x1, so I got 235 minus the mean, 225. Divide that whole thing by 7.5. And this value, I assure you, is equal to something, 1.33. We do the same thing over here. I've got z2. This case, it's going to be x2 minus mu divided by sigma, which is going to be, here's our x2, is 220. So 220 minus the mean, 225, divided by 7.5. Get that darkened up. And this one here is going to be equal to 0.667. Let me warn you. Sometimes when people calculate z values, they will get a number that's less than 1. And they will think, I've found a probability. No, you have not found a probability. You have found a distance. This is the distance that the x value is from the mean value. So this is 0.667. Now what we do is we look up the value in the z table. And this one here is 0.4082. And this value here is equal to 0.2486. Okay? So that's what this area is here, and that's what this area is here. We, of course, want the sum of those two numbers. So the answer to our question is equal to 0.2486 plus 4.4082. And that happens to be some number that I've written down over here, 6568, 0.6568. Okay? Calculating probabilities for a normal distribution is always helped by drawing a graph of the distribution. We can set up the probability we are after on the x-axis up here, and the probability on the z-axis down here for the standard normal. Tying the graphs of the variable we are interested in to the standard normal graph helps keep track of the logic of the process and makes the problem much easier to solve.